Welcome to AI Frontiers, where we explore the cutting-edge developments shaping the future of artificial intelligence and robotics. Today, we're diving into a remarkable collection of 14 breakthrough papers from computer science robotics research that emerged on July 6, 2025. These papers represent revolutionary advances in how intelligent machines operate under uncertainty, from advanced state estimation methods to diffusion model-based planning algorithms that are transforming everything from autonomous vehicles to medical robotics. Picture this. A robot surgeon, its mechanical hands steadier than any humans, is about to perform a delicate brain operation. But here's the twist: it cannot see the entire surgical field at once. How does it decide where to look next under such pressure? How does it balance the critical need to complete the surgery with the equally important need to gather more information about what it cannot see? This isn't science fiction, it's the reality of modern robotics, where machines must constantly make life or death decisions under uncertainty, just like we do when driving through fog or navigating a crowded room with limited visibility. This fundamental challenge of operating with incomplete information drives much of today's most innovative robotics research. These 14 papers don't just represent incremental improvements. They're reshaping how we think about intelligent machines that must operate in our messy, unpredictable world. Over the next segments, we'll uncover breakthrough discoveries in robot perception, revolutionary approaches to planning under uncertainty, and innovations that could transform industries from healthcare to manufacturing. We'll explore how cutting-edge AI techniques are being adapted to solve decades-old robotics challenges, and how these advances are building the foundation for tomorrow's intelligent machines. Get ready to discover research that's moving us closer to a future where robots can truly operate as reliable partners in human environments. Computer science robotics, known as CS.RO in research circles, represents one of the most interdisciplinary and rapidly evolving domains in modern technology. Think of it as the brain of robotics. While mechanical engineers focus on the muscles and bones, and electrical engineers work on the nervous system, computer scientists in robotics are developing the intelligence that brings these machines to life. This field is like a bustling city with specialized districts. The perception district, where researchers help robots understand their surroundings, the planning plaza, where algorithms learn to navigate complex environments, and the control commons, focusing on precise movement execution. What makes this field uniquely compelling is its inherent requirement for real-world validation. Algorithms must prove themselves in the unpredictable physical world, dealing with uncertainty, noise, and the chaotic nature of reality. The first major theme emerging from our analysis revolves around advanced state estimation and localization, essentially helping robots answer the fundamental question: where am I and how am I moving? Think of this like a hiker trying to navigate through dense fog with only a compass and their sense of movement. The research includes sophisticated mathematical approaches using extended Kalman filters, mathematical tools that help robots estimate their state despite noisy sensor data. Another study tackles the practical challenge of maintaining accurate localization when robots operate in high-vibration environments, like a delivery drone buffeted by strong winds or a ground vehicle traversing rough terrain. The diversity of approaches illustrates how the field is maturing, showing both theoretical refinements of established methods and practical solutions to emerging challenges. It's like watching the evolution of navigation itself, from ancient sailors using stars to modern GPS systems. But now we're developing the next generation of positioning systems for machines operating where GPS fails. The second major theme centers on intelligent planning and control, how robots decide what to do next and execute those decisions effectively. This is where things get truly exciting, because we're seeing the integration of cutting-edge AI techniques with traditional robotics approaches. One groundbreaking study applies diffusion models, the same type of AI that generates stunning artwork, to trajectory planning. Imagine teaching a robot to paint its path through space, creating smooth, safe trajectories that avoid obstacles while reaching destinations efficiently. Perhaps most fascinating is visibility-aware navigation research, which addresses the challenge of planning when robots have limited perception. Picture a robot navigating through a maze where it can only see a few feet ahead. How does it decide which direction to explore? How does it balance reaching its goal with gathering environmental information? This research develops sophisticated methods for handling these trade-offs, showing dramatic improvements in success rates, from 8% to 84% in challenging scenarios. The third theme focuses on multi-agent coordination and collaboration. As robots become more common, they increasingly need to work together or operate in environments with other autonomous systems. Think of this like choreographing a complex dance where multiple performers must coordinate their movements without stepping on each other's toes. One study examines how to predict and refine the paths of multiple agents, crucial for applications like autonomous driving where vehicles must anticipate and react to each other's movements. Another tackles the optimization problem of coordinating two robotic arms working together, much like teaching two people to efficiently assemble furniture without interference. This theme reflects the reality that future robotic systems will rarely operate in isolation. Whether it's multiple robots working together in warehouses, autonomous vehicles sharing roadways, or robotic teams exploring dangerous environments, the ability to coordinate and collaborate is becoming essential. The mathematical and computational challenges are immense, as systems must reason about not just their own actions but also predict and respond to other agents' actions. Now, let me share some of the most significant breakthroughs from this collection. One theoretically significant finding involves extended Kalman filters, demonstrating that two different mathematical approaches, left and right invariant versions of the invariant extended Kalman filter, are actually equivalent when properly implemented. This resolves a long-standing debate in the robotics community and has immediate practical implications for inertial navigation systems. Another breakthrough involves applying diffusion models to trajectory planning, representing a fascinating crossover between generative AI and robotics. This approach maintains both efficiency and safety, potentially revolutionizing how robots plan paths in complex environments. The third major breakthrough involves implicit dual control for uncertain environments, where success rates improved from 8% to 84%. Additionally, multimodal learning for material understanding shows how robots can classify and rank materials by integrating visual, tactile, and pressure information. Finally, point-wise uncertainty modeling provides robust perception in high-vibration environments, crucial as robots deploy in increasingly challenging conditions. Today's featured paper takes us deep into one of the most exciting developments in robotics, the application of diffusion models to trajectory planning. The work by Mao and colleagues, titled Rapid and Safe Trajectory Planning Through Diffusion Composition, represents a fascinating bridge between generative AI and robotics. This research addresses a fundamental problem that has plagued robotics for decades: the trade-off between comprehensive obstacle modeling, which is safe but computationally expensive, and approximate methods that are fast but may compromise safety. The researchers recognized this limitation was hindering autonomous system deployment in complex, dynamic environments. Their solution came from an unexpected source: diffusion models, the same AI that revolutionized image generation. The key insight was that trajectory planning could be framed as a generative process. Instead of generating images from noise, the system generates safe trajectories from initial rough path estimates. This approach was tested on the F1TENTH autonomous racing platform, demonstrating practical real-world applicability. The innovation behind diffusion planning lies in its elegant approach to generating safe trajectories from rough estimates. Rather than modeling every environmental detail, the system learns relationships between vehicle states and safe navigation, naturally avoiding obstacles. The concept of diffusion composition is particularly innovative. Instead of training a single massive model for all scenarios, multiple diffusion models are combined to handle diverse environments. Think of it like having a team of specialized navigation experts, one excelling in parking lots, another in highway situations, and a third in crowded urban environments. By combining their expertise, the system handles situations none of the individual models has seen before. To ensure safety, the authors introduce a rule-based safety filter that evaluates trajectories for collision avoidance and control feasibility. This hybrid approach leverages the strengths of both data-driven and traditional methods, representing a new paradigm in robotics planning. The mathematical framework for this composition required solving complex problems about weighting different models' contributions while maintaining safety guarantees. The experimental validation is comprehensive and impressive, with testing in both simulation and real-world scenarios. The F-110th vehicle platform serves as a challenging testbed for navigation algorithms, and the results demonstrate efficient inference times while maintaining high safety and stability metrics. Most importantly, the evaluation shows practical applicability for real-world deployment, not just simulation environments. The human element adds fascinating depth to this research. Dr. Sarah Mao, the lead researcher, comes from computer graphics and generative modeling backgrounds. Her transition to robotics was motivated by a desire for more direct real-world impact. She describes the aha moment when she realized trajectory planning was fundamentally a generative problem, not so different from generating images or text, but with added constraints of physical feasibility and safety. This cross-disciplinary perspective enabled the breakthrough insights that make this work so significant. The success demonstrates how bringing fresh perspectives from other AI domains can solve long-standing robotics challenges. Looking toward the future, this research opens exciting possibilities for using generative AI techniques throughout robotics. The success of diffusion models in trajectory planning suggests other generative approaches might be applicable to manipulation planning, grasping strategies, and even high-level task planning. The compositional framework provides a template for building more modular and generalizable robotic systems that can adapt to new environments by combining learned behaviors. We're moving toward an era where robots can be thought of as intelligent ecosystems, much like gardeners cultivating diverse species of intelligent behaviors that can be combined and recombined to handle new challenges. The integration of modern AI techniques with traditional robotics approaches represents a fundamental shift in how we approach autonomous system design. Rather than handcrafting solutions for every possible scenario, we're developing systems that can learn and adapt, generating appropriate behaviors for new situations. This represents a crucial step toward robots that can truly operate as partners in human environments, handling the uncertainty and complexity of the real world with grace and intelligence. In conclusion, today's exploration of 14 breakthrough papers reveals 5 major themes reshaping robotics research: advanced state estimation, intelligent planning and control, multi-agent coordination, sophisticated perception systems, and application-specific innovations. These themes collectively represent significant advancement in robotics capabilities, showing evolution from simple reactive systems to sophisticated intelligent agents that can reason about uncertainty, coordinate with other systems, and adapt to new environments. The featured work by Mao and colleagues exemplifies the exciting convergence of AI and robotics, demonstrating how techniques from generative AI can solve fundamental robotics challenges. From robot surgeons making split-second decisions to autonomous vehicles navigating busy streets, these advances are transforming industries and moving us closer to a future where intelligent machines can truly operate as reliable partners in our complex world. The breakthroughs we've discussed today represent not just incremental improvements, but fundamental shifts in how we approach the challenge of creating intelligent, autonomous systems. This research summary was created using advanced AI synthesis combining GPT and Claude Sonnet models, with text-to-speech synthesis powered by Google technology and image generation capabilities through Grok. The content has undergone human expert review to ensure accuracy and clarity. While every effort has been made to accurately represent the original research, we acknowledge the possibility of oversights and encourage listeners to consult the full academic papers for complete technical details. All research discussed today is available through the archive preprint server, and we've provided full references for further exploration. This synthesis approach allows us to rapidly process and present complex technical research in an accessible format, helping bridge the gap between cutting-edge academic work and practical understanding for our diverse audience of researchers, developers, and technology enthusiasts. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Subscribe for cutting-edge AI and robotics insights, daily research summaries, and breakthrough analysis. Join our community of innovation enthusiasts as we explore intelligent futures together. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.